This first problem is designed to give us practice applying what we learned with monohybrid crosses to dihybrid crosses. So we'll say that we have 3 genes and that we have individuals that are heterozygous at all 3 of those genes. So we just need to take our monohybrid results and then carry those across 3 separate genes. So for 2 heterozygous individuals, an offspring that would be recessive would be 1/4. So now we have for 3 separate genes, 1/4 to the 3rd power. So that would be 1/64. In this second problem, once again, we're looking at multiple genes, but in this case, one of our genes is a standard autosomal recessive gene, and then the other one is the gender of the offspring. So at the end of the day, we're asking what proportion of the offspring would be a carrier and a female. So first we have to figure out what proportion would be a carrier, and to do that we have to start off by saying that we had a normal male and an affected female. So for the normal male, we don't know what his genotype is, so we're going to say he's big A dash. But if he produces a daughter with a dominant phenotype, then she would have to be a heterozygote because her mom is affected. So that daughter goes on to have offspring with a carrier male, so now we have a cross between 2 heterozygotes. And the probability that a cross between 2 heterozygotes would produce a carrier offspring would be 1/2. And all crosses between, at least in mammals, between male and female will produce half male and half female offspring. So we have our 1/2 for our autosomal recessive gene, and then we have our 1/2 for our gender chromosomes. So 1/2 times 1/2 equals 1/4. This problem is much like the very first problem, except in this case we're crossing a homozygous recessive parent with a heterozygous parent, and so we're going to say that there are 3 separate genes, and we're going to look at the probability of them producing a child in the F1 with a completely dominant phenotype. So for one individual cross, one individual gene, the dominant phenotype would be 1/2 of their offspring. So when we carry that across 3 separate genes, it's going to be 1/2 to the 3rd power, so it'll be 1/8. This problem becomes a little bit more complex because now we have multiple genes and we have a different phenotypic result that we're looking for in each of those genes. So we want to know what probability of what proportion of the offspring would be yellow and white. If we have 2 separate genes controlling seed color, they could be yellow or green, and flower color could be purple or white. So the first thing we do is cross the G locus, and so we see that that's a cross between a heterozygous and a homozygous recessive. So 1/2 of the offspring would be yellow. And then for our other locus, we cross homozygous recessive with heterozygote. And once again, we see that 1/2 would be little p or white. So now we multiply across our different genes, 1/2 times 1/2, and we should get 1/4. In our fifth problem, we're only looking at one single locus, but we're looking for genotypic ratios instead of phenotypic ratios. So the difference is subtle but important. If we were to do this with multiple genes, the same thing would apply as to the previous problems. But in this case, we're crossing 2 heterozygotes, so we generate our genotypes, and we see that 1/4 are homozygous dominant, 1/2 are heterozygous, and 1/4 are homozygous recessive. So those are our genotypic ratios and not our phenotypic ratios. Our phenotypic ratios would have been 3:1. And in our last problem, we're doing a chi-squared test. So we're only going to do a monohybrid cross to keep things simple, but the same rules would apply if we were doing multiple genes. So for this particular problem, it's asking us what our chi-squared value would be in our F2 generation, and it's giving us our parental generation, which means that we first have to generate our F1 before we can generate our F2. So our parental cross is homozygous recessive with homozygous dominant. That gives us all heterozygous individuals in the F1. If we cross those individuals in the F1, then we can get our F2, where we have our standard 3:1 ratio. That means that in our F2, we should see 3/4 of the offspring yellow and 1/4 green. Now we'll say that our observations in this case are that we have 25 yellow and 15 green. And we need to know if our expectation is different from our observation. So if 3/4 should be yellow and 1/4 should be green, then 30 should be yellow and 10 should be green. So that means that our standard formula for calculating chi-squared, which is observed minus expected squared over expected, summed across all classes, means that we're going to have 30 minus 25 equals 5. 5 squared divided by 30, and 5 squared divided by 10. So if we do some quick math, we see that 25 over 30 equals 5/6, or 0.835, and 25 over 10 equals 2.5. We add those together to get 3.335. That's less than our critical value of 3.84, so our results are consistent with our expectations. Our observations do not significantly differ from our expectations.